Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers, and we'll extend our discussion on level measurement. Previously we discussed level measurement using magnetostrictive and piezoelectric sensors. In this video we're going to discuss the same but with strain gauge sensor. So we have discussed about strain gauge previously in detail. Here we'll just go through it in a quick way. First, what is a strain gauge? It is a primary transducer. Again, I remind you, primary transducer is one which converts any physical parameter such as displacement, mainly force, pressure, whatever it is, into some mechanical movement, linear or rotational motion. Then we have to connect another secondary transducer which is of electrical nature, electrical transducer, to convert that mechanical movement into voltage or current signal. Commonly used secondary transducers are LVDT, resistive transducers such as potentiometers, or capacitive sensors, inductive sensors. Those are commonly used secondary electrical transducers. The secondary transducers are mostly electrical in nature. So strain gauge is a primary transducer which is connected in the first stage of the sensing mechanism. So strain gauge is used, as I said, it is used for measurement of stress, strain, displacement, force, pressure. Here we'll be utilizing that principle to measure liquid level in a container. How we'll do that, we'll see. So the basic operating principle of strain gauge is based on the principle of piezo-resistive effect. We all know the resistance of a material is given by R is equal to rho L by A, where rho is the resistivity of the material, L is the length, and A is the cross-sectional area. So here the resistance is directly proportional to the length, directly proportional to the resistivity, and inversely proportional to the cross-sectional area. So when area increases, resistance decreases, and when area decreases, resistance increases. Okay, that. Here it is directly related, so materials with high resistivity will have high resistance, and when length increases, resistance increases, when it decreases, it decreases. These are the basic principles. Now, the variation of resistance with change in length, that is increase or decrease in length, when the length of a material is changed, whether it increases or decreases by a certain margin, let's say delta L, the variation of resistance is something like this. Okay, as it is directly related, an increase or plus indicated by plus in length, change in length delta L, contributes to an increase in resistance delta R, and a decrease in length, which is indicated by minus, contributes to a decrease in resistance by delta R factor. Okay, area and resistivity, they are constant. Similarly, for cross-sectional area, here you will see it is opposite. See, here it was plus minus, same order. Here it is minus plus, plus minus. Why? Because resistance is inversely proportional to cross-sectional area. So an increase in area contributes to a decrease in resistance, plus minus, plus delta A minus delta R, and a decrease in area by factor delta A contributes to an increase in resistance by delta R. So this is the basic principle. So another thing, how this thing operates, generally what we have is that this is the basic design. The whole arrangement is placed inside a box or encapsulation to protect it from external pressure, temperature, and other effects, wear and tear, all that. So this is the strain gauge arrangement, which basically comes in this form, where we have some kind of base on which the resistive wire is wound over it, and the extensions are given, and it is arranged in this kind of arrangement where each strain gauge is at an angle of 45 degree with respect to the other, mutually in that angle. The whole arrangement is placed like this, okay, and each of these wire extensions are connected to the connecting rod via the sensing shaft. So the force, pressure or any kind of displacement that is focused here on the sensing shaft. So when it is subjected to any force, pressure, displacement, stress, anything, it undergoes movement, and that movement is passed to the strain gauge through the connecting rod, and as a result of which these wire extensions, they either undergo compression or expansion. And when they undergo compression or expansion, there will obviously be an increase or decrease in length or increase or decrease in cross-sectional area. And as a result of that, they undergo change in resistance, and that change in resistance can be converted into suitable voltage or current signal through either voltage divider mechanism, through Wheatstone bridge, or it can be connected to a secondary transducer, as I said, through a potentiometer. Basically potentiometer resistive transducer is used, so it can be converted to a voltage or current signal through that way. That is the basic principle. So here when the material is subjected to force, as I said, it undergoes compression and expansion. When it undergoes expansion, there is an increase in length and decrease in cross-sectional area, and when it undergoes compression, there is a decrease in length and an increase in cross-sectional area. And when it is subjected to any kind of force or pressure, it undergoes movement, and that contributes to a change in the resistance because of compression and expansion of these wire extensions, which are connected to the 4 strain gauges, which are connected at an angle of 45 degree with respect to each other. Okay, now there are 2 important parameters which are associated with strain gauge. Basically, with piezoresistive effect, there are 2 parameters. First, Poisson's ratio and gauge factor. So what is Poisson's ratio? As I said, when any material is subjected to any kind of force and undergoes compression and expansion. In compression, cross-sectional area or diameter, that increases and the length decreases, and in expansion the length increases and the cross-sectional area, which is measured through the diameter, that decreases. So Poisson's ratio gives us the ratio between the lateral strain and the longitudinal strain, which is lateral strain is per unit change in diameter divided by the original diameter, that is lateral strain. Longitudinal strain is per unit change in length divided by the original length, and there is a negative sign. And when we take the ratio, we will be left with this: per unit change in diameter by per unit change in length. Okay, that is the whole thing of Poisson's ratio, lateral strain by longitudinal strain. Then gauge factor is the ratio, as I said, when length and cross-sectional area, they undergo change, resistance will undergo change, but gauge factor measures the ratio between the change in resistance and change in length, which is the per unit change in resistance divided by the per unit change in length. Per unit change in resistance is the change in resistance divided by the original resistance divided by change in length, a small change in length divided by the original length. Okay, dr by r divided by dl by l, where dr and dl are small changes in resistance and lengths, and R and L are the original resistance and original length of the material. So this is gauge factor and this is Poisson's ratio. So there is a relationship between gauge factor and Poisson's ratio, just remember it. It is, gauge factor is twice of Poisson's ratio plus 1. Okay, GF, which is gauge factor, is equal to 1 plus 2 nu, which is nu is Poisson's ratio. So these are some of the commonly used materials for strain gauges with their resistivity and gauge factor given. First is Constantan, resistivity 48, the unit is given, mentioned here, and gauge factor, which is it has no units, so it is 2.1. And then nichrome, it is 100, and the gauge factor is 2.1 to 2.5. Okay, and nickel, it has resistivity 6.5 and gauge factor minus 12, and platinum, it has resistivity 10 and gauge factor 4.8. Okay, so this is the whole thing. Okay, then as I said, signal conditioning can be done through Wheatstone bridge or voltage divider, and then that signal is fed to suitable amplifiers, signal conditioning circuitry, and then to the output through proper analog to digital conversion to give us a proper digital output. This is the basic operating mechanism of strain gauge. Now how we can use it to measure liquid level in a container. Now there are various ways in which we can use strain gauge. First, the float and rod arrangement, that is fixed. Any kind of sensor you use, the float and rod arrangement is there. That is constant. But how we connect it to the sensor, how we convert that change in level to to affect the sensor, that depends on our on our choice, the operating conditions, the surrounding environment, everything determines how we use that sensor to measure the particular physical parameter. So this is the first way. Here the strain gauge is connected to the rod attached with the float, okay, and it is connected to this sensing shaft which I shown you in the first. Okay, this, it is connected to the sensing shaft here. So whenever the liquid level, it goes up or down, the rod attached with the sensing shaft of the strain gauge, it also undergoes movement, and as a result, via the connecting rod which is attached to the strain gauge here, the 4 wires, 2 of them undergo compression, 2 of them undergo expansion, and as a result of this there is a change in resistance. That change in resistance is converted to voltage or current signal and get a proper voltage or current signal output. This is the first way. Then we have the other arrangement where again, like we have used in all the previous sensors, again float and rod, and we connect the sensor, the strain gauge sensor, at the the side walls of the container. So when the liquid level in the container, it goes up or down, the rod attached to the float, it strikes the sensing shaft of the strain gauge sensor, and as a result, again the pair of wires in the strain gauge via the connecting rod, they undergo expansion, and the other pair, it undergoes expansion. Change in resistance contributes to a voltage or current signal. This is a single sensor arrangement where only one level alarm is there. Generally the danger level, where we don't want the liquid level to go above a certain level or below a certain level, like that. So it generates alarm for only one level because only one sensor is used. And we can also connect a series of strain gauge sensors depending upon the requirement, 2, 3, 5, 10, 15, whatever, depending upon the length of the container and the requirement, and the number of measurements that we want. Okay, that. So depending on that, we can connect as many strain gauge sensors. This gives us continuous level tracking. The operating mechanism is the same. As the liquid level, it goes up and down. The rod strikes the sensing shaft of the strain gauge sensors, and that generates the signal. Okay, so this is the basic operating mechanism of liquid level measurement using strain gauge sensors. Okay. So let us try to understand this whole thing from a 3D perspective. So this is the arrangement where we have to measure the liquid level in a container. This is a single sensor arrangement. The liquid level is there. So when this whole thing along with the liquid level, it goes up and down and strikes the sensing shaft, this shaft which is connected to that which is connected to the strain gauge arrangement, it undergoes compression and expansion. Okay, so it undergoes movement. Okay, and that results in compression in a pair of wires and expansion in the other. So when it undergoes expansion, there is an increase in length and decrease in cross-sectional area. And when it undergoes compression, there is an increase in area and decrease in length. So that contributes to a change in resistance, and that change in resistance can be converted into voltage or current signal through voltage divider, Wheatstone bridge, or use of secondary electrical transducers such as potentiometer, LVDT and other. This is the single sensor arrangement, and this is the multiple sensor arrangement. So whenever the rod, it strikes a particular sensing shaft, that particular sensor is triggered and it gives us information about the level of the liquid. Now, all in multi-sensor arrangement, the sensors are connected at fixed separation gaps with respect to each other, so that whenever a particular sensor is triggered, we can give exactly the location or the level of the liquid at that position. And most of the cases, the length of the rod attached to the float is negligible as compared to the level of the liquid which is being measured. So this is a few centimeters and this is several hundred meters. So it is negligible, so it can be neglected, and in some cases it is subtracted to give us more accurate and precise measurements. So this is the whole thing related to liquid level measurement using strain gauge sensors. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.